So my name's Luis. I'm an AI machine learning engineer for Boeing.
My name's Taylor Loper. I'm a software engineer for the Boeing company. Oh wait, do we go? Sorry. You should be able to tell how good of an engineer I am by how bad I am at presenting. Me and Luis I've been using the Unreal Engine for about a little over 12 years when it first came out as a subscription service. I actually learned it by watching Epic's YouTube videos as they released, which is it was possible to do back then. Now there's so many tutorials, like to consume it all is impossible. Me and Luis have we've worked in the AI field for a number of years now. We hold patents and we publish papers. But we're not actually here to talk to you about AI or ML or neural networks. We're going to talk to you about something much more interesting, and that's data, how we generate data. And this might feel like a lab. Sometimes we're going to go over some of the technical stuff and some actual code. But we just wanted to give you an idea of like how to generate a pipeline. So one thing to understand is there's a number of kind of overlapping domains here that make this possible. So just to start at the bottom, the ground truth or digital twin. This is, when we talk about this in this presentation, we're really talking about like an authoritative source of truth. So that might be a sensor reading, might be an IMU, might be a digital elevation model, a CAD model. CAD model is used in production. And then, just kind of linking that to the digital twin. Now, when we talk about simulation, like when I say sim or simulation, we're using the Unreal Engine to simulate the visible light spectrum. So that's the simulation we're doing here. And that includes, so it kind of lines up 3D rendering, right? So that's your geometry, your materials, and your lighting. And then camera emulation or virtual production. This is an area Epic has made, they put a lot of effort into this over the last few years. I'm sure everybody is, familiar with The Mandalorian. They've just made great strides in this, and we've leaned very heavily on that technology. They'll call it virtual production. We call that hardware emulation or camera emulation in kind of the engineering field. So basic knowledge requirements. It was kind of hard to figure out the target audience for this. It's just a lot of data. I don't expect everybody in here to be an expert in each one of these bullet points, but we'll touch on each one of them. We essentially tried to gear this towards, possibly you're either a data scientist and you're familiar with the Unreal Engine, but you might not know the full process of generating synthetic data, and you have a data need you think it can resolve, or you might be an expert in Unreal and you're supporting an AI or ML team as a sort of supplier for data. All right, so we're going to talk about why we use synthetic data. Obviously, that's important, and then we'll just go through some steps on how you import data, the prepping of assets, populating sequencer, and then actually getting that data back out in the form you want. So why use it? The first is cost. So as you might be aware, there's kind of when you start off, you're either going to you have data, or you're going to pay to acquire data, or you're going to pay to have that data labeled, right? So that might be just starting from the cheapest is classification, and then you've got bounding boxes for object detection. Then you've got segmentation masks, and then probably pose estimations is the most expensive. Generally speaking, that work is usually outsourced to a third party. But if you have any type of data controls, if that's proprietary data, if that has any type of earmarking, is export controlled, ITAR, any higher levels of classification, and that cost skyrockets. And then scalability, assuming you have a prototype, right? I need to track 2 classes and I need 10,000 images just to see if this thing works, right? You do it, it does work. Now I need 10 classes and 1 million images. The ability to scale like that is very possible using synthetic data, especially with the Unreal Engine. Hardware procurement's another one, right? So, a lot of times we kind of put a camera in a place and we look at the field of view and we make a best guess, is this camera going to do it? We're able to load these cameras into a virtual scene, render the CAD models. We can see exactly what does that camera see. Does that camera see what I need it to see? And that really helps you whittle away at hardware procurement. You might start with 100 cameras, you end up with 6, and then you load those 6 in, and you're like, okay, what does this see the actual thing I need it to? And then digital twin, obviously you'll hear this in presentation after presentation, but it's a pretty big deal. The digital twin is essentially the ability to tie this data back in and your physical twin to benefit from that, right? So we kind of always say build the game first, or electrons are cheap. This lets us fail in the lab, right, and not with the physical hardware. So next is data scarcity. It may not be a money issue with the data. You may have all the money in the world. The data may just not exist. So you might be working with a camera that is in development, hasn't been released yet. You might be working, with scheduling. There's risks. So if we need to do a flight test, right, we kind of schedule out a flight test. There's risks to that. The weather might cancel that flight, right, and then that flight gets kicked back a week or two, right? That's a week or two of wasted. Well, not wasted time, but right, it's kind of twiddling your thumbs. That doesn't happen with synthetic data. The speed of data generation, that kind of speaks for itself. It's very fast. And then future data gaps, this is where it gets really weird. So if you have an authoritative source of truth, again, just taking a CAD model, for example, right, where we have a new component and we are going to install that component in a system. And we want to be able, but that component hasn't been manufactured yet. But we want to, the day it arrives at our factory, we want to track that component through the factory until it is installed, in the system. We can actually train a model to recognize something that nobody's ever seen before, right? Because hasn't been built yet, right? So we can have this kind of sort of like day zero functionality to recognize objects that again haven't been created yet. Interoperability, hardware changes. A lot of times if you upgrade a system, you don't just throw the old system away and start from scratch, right? You're going to upgrade sort of components of it. You're going to study it. You're going to see what you can keep, what you can get rid of. Assuming you're just updating the camera, again, this kind of ties back into that hardware procurement. The ability to change portions of that system and test out. The accuracy, if you're familiar with computer vision, this might mean more to you. For better or worse, your labels will be perfect. So just be aware of that. And then operational design domain, which Luis will talk to you here in just a moment. Once you start generating synthetic data, it's very easy to just run, right? I mean, it's to go from, here's 100 images, I can generate 1 million images, and I've got labels for all of them. If you don't have this defined, you'll end up with a lot of, essentially just worthless data. Like it's very easy to, it's very important that you sort of define your issue. And then lastly, just again to be aware, if you control the data, you control the bias, right? If there's a bias in your model, you can almost always tie it back to the data. All right, now Luis is going to cover the operational design domain.
Okay. So just what is this? What is an operational design domain? So I'm going to talk about this just in the context of like a real world example. So outside of the engine, outside of any of this stuff, one concept in computer vision is you define your space first. A lot of times, especially in computer vision, your system is an n-dimensional space, or an image can be, depending on your view, there's n dimensions, there's lots of pixels, lots of combinations. So we got to parameterize our system. And so we do that first. We think in this case, our system is air refueling. So this is a KC-46 airplane. In the bottom images there, you see that vertical thing with wings. It's basically a pipe with wings. That's what connects to the receiving aircraft to pass fuel midair. So we have, obviously a boom, another airplane. We have its position and orientation. We have the way the the materials look. We can have a brand new leading edge, a worn in one. We fly over different terrain, and the sun can be in different positions affecting the image. So this is all important to parameterize outside of Unreal. And then once we say, okay, well, we expect the airplane to roll plus or minus 5 degrees, during air refueling. Now we have a range, and then we can map that to Unreal and create these images. So in this case, we got receiver, we call it receiving aircraft pose, materials background, some positions. So and then we can even do the night stuff. So we can model the lights and illumination and how that looks in Unreal. So all controllable in Unreal to be able to map our operating space. So here's a flight condition. So I guess, show of hands, who thinks the left image is real versus who thinks the right image is real? Okay, so it's the left image is real. Yeah, you kind of maybe noticed that. Good thing I said that quick. So this is important. We want test data that represents our space. So we can fly the real condition, create it in Unreal. So here we use the aircraft pose from the flight data, the materials from the paint specs, so we can, and there's some more work to be done on that, but that it looks representative, the color. We get the lat-long altitude from the GPS buses on the airplane to get that geospatial position. And then we can get the sun from the time of day. So you can see the shadows are lining up. We're flying over the same terrain. And so now we have representative test data to model our system and then to test our computer vision algorithms. Okay, so now I'm going to hand it over back to Taylor. We're going to talk about how we get data in the engine.
I'm curious about some of those hands, because I feel like every time we ask people that, they think we're trying to trick them, and they see the left one, they're like, that looks too real. They're trying to trick me. So there might be a little bit something there. All right, so we're going to import data. All right, data comes in obviously all kinds of forms and sizes. We're just going to use a CSV file for this, right? Everybody recognizes this. This is a CSV file open in Excel. You've got your index. We're going to use these X, Y, and Z values to populate, to add sockets to a static mesh. Roll, pitch, yaw, just random lat long has all been zeroed out. You can ignore that. When you're actually working with real data, though, so we're going to convert this to a data table, and we're going to use Python to do that. And there's a few benefits to that. One is, these data tables are in binary format. They're very fast to read. It makes it viable to read that at runtime. And there's also type safety. When you're dealing with massive amounts of data, it's a very good thing to have. And just generally, again, this is very simplified, but you might have a couple hundred columns and tens of thousands, if not hundreds of thousands of rows. That's the data you're ingesting, and Unreal Engine can handle it. So if you see up here at the top, we've just got an editor utility button, right? So we use these editor utility widgets. User clicks the button. It goes in and it reads a very specific. This is a hard-coded Python file, right? That example CSV import.py. We read the text and then we feed this little execute Python script. So just out of curiosity, how many people here know that the Unreal Engine ships with an embedded version of Python? That's awesome. It is so powerful. It's so cool. So I mean, here you can see we're feeding it 2 arguments. We're feeding it where the CSV file is, and we're feeding it where we want that data table to save out, right? And then here's again just a very simple Python script of what that's doing, right? We pass those arguments in, and then we load. We've already defined a struct, which is again just basically the column names that you saw. We read that in, and then we save that. Then we save that as a data table. All right, now prepping the assets. Again, very similar to what you saw, but in this case, we're getting the actor. We're getting the selected actor. We're just getting the first one that you selected. These are editor functions, right? So you won't be able to package this into a game, right? This is kind of fixed to the editor, just to make that clear. And then, we're getting the static mesh. We're getting the actual directory location of that asset, and then we're going to save it as a string. The next thing we do is we go and we read every single line of that data table, and we take the X, Y, and Z, and we package those into an array of vectors. Then, just like before, we read that into this execute Python script, but we're passing it an array of vectors and a string. And the reason we use that read text node is it lets your developers develop Python in whatever IDE they're comfortable with, right? So you don't have to do it in the engine. You use Visual Studio Code, whatever you're comfortable with, right? We read it in when you're done. And the idea that, you can see here, just the sheer fact that you can pass an array of vectors, like you can start to imagine what you can do with that. And additionally, you can get arguments back out of Python. So you might do your analysis in Python, right? And then you get, an array of, maybe those are, a point cloud or whatever it is, you can get that data back out of a Python script. So that integration is very useful. What this Python script does, again, it just takes that vector array, we passed it. We turn it into an actual Unreal vector, just again for type safety. We load the location of the mesh, and then for each one of those vectors, we are creating a key point. You'll see line 15, key point underscore, and it's just an index. Right, so here I think we're adding 8, right? So you have key point 0 through 7. I just point that out because you can use this to put key points for different purposes. You can have, well, let me go to the next slide, right? So this is the end result. We read in the CSV file, and now we've added sockets to a mesh. You can, again, if you do this sort of analysis in Python, you might come up with different points for different use cases. So like maybe you want to segment out a portion of the aircraft, right? So I want to get a bounding box around just the engine, right? So you could, you name those key points, engine, right? And then, engine 1, engine 2, whatever that is. We'll use them for bounding boxes. We'll use them for key points. So we use them for key points here to do a key point detection and a pose estimation, right? So we're trying to get the pose of that aircraft, right? So we can use those sockets. We know where they are. They're tied to vertices on the aircraft. And then we can, we have a model that can inference against those images and give us a pose of the aircraft. What am I missing here? Yeah, okay. Okay. And Luis is going to talk to you about populating the sequencer.
Okay. I'm the AI ML guy. I'm not the Unreal expert. So I'm going to butcher some of the following stuff. But Taylor mentioned that you guys might like the spaghetti graphs. What Taylor showed you was kind of a simplified example of getting data in using Editor Utility Widgets and blueprints to do something with that data. And so here we're doing much more stuff with this data. So this is representing how we're taking a CSV file, we're importing it, and then we're feeding that information to all of our actors in our scene. So it can be the receiving aircraft, the boom position, the georeference, the position of the sun, or the orientation of the sun. So it goes through all of those nodes, with just the click of a button. So just to kind of show you guys the complexity that we're able to achieve thanks to the Editor Utility Widgets. And so now what we'll do is we'll zoom into one of these sections and see how we can set an actor's position. Okay. So here we set up our sequencer, and we've got some actor with its transform there. So this assumes that we already assigned possessables as a movie scene binding proxy type. But we'll navigate through the tracks to add position and orientation keys. So next we'll get the movie scene 3D transform track. Then movie scene section. And then the channels. And those are color labeled there below in the sequencer. Those channels end up here. So once we get the channels of our actors transform, then we can add a keyframe with the values from the data table that we imported. So there's a lot of stuff here, but essentially all you're doing is we're setting the frame number, we're setting the value of that keyframe, and then we're setting an interpolation type. There's more to talk about with interpolation methods, but essentially if your sensor rate matches the rate that you're trying to make data in, 30 frames a second, we just set it as constant. And if they're different, then there's other things that you can do. Another thing to note is we leverage the blueprint function libraries to consolidate all of our calculations and logic that spans our entire project. So if you guys are in computer vision, coordinate transformations are a big thing. Easy to throw them in there and have a library that does all that stuff. Here we have a simple feet to centimeter conversion contained in a macro. So we're only showing the X and Y positions here, which would be channels 0 and 1. But the Z position would be channel 2, and then roll, pitch, and yaw would be channels 3, 4, and 5. Okay. So actor blueprints. So we like to store that functionality for that actor in its blueprint. And then custom events and functions defined in that blueprint can be accessed through sequencer. What's nice about that is it allows you to maintain logic in sequencer as well as runtime applications. So like offline rendering in sequencer or real-time, runtime applications. And the example here is where in this actor for this receiving aircraft, we have functions to set the lights. So we added all the lights. We added the IAS profiles, which, by the way, is super great functionality. All we have to do is talk to our engineering team and lights for the aircraft, and they gave us all the profiles, and we just drag and drop them into the engine, into our project, and they just worked. So super great functionality. So we have those functions that control the lights, that dim the lights, and then we can call them in sequencer using events. And we can even do things like triggering the floodlights based on time of day. So because we're also controlling the position of the sun, when it gets too low, boom, the lights come on. Yep, okay, cool. So now we'll talk about, so we talked about getting data in, doing stuff with the data. Now we're going to talk about getting data out in the form of exporting images and labels. Okay, so we use a blueprint actor called the metadata manager to centralize all of our world parameters. So this can be things like the georeference and the sun, but also to collect and manage all of our labels and annotations. So you can see there we have an aircraft to put a box around it, and as Taylor was mentioning, we use the sockets. So we have sockets that, we find the screen space limits of those sockets. So we use a 3D to 2D calculation to get the screen space. And then we found those boundaries, we create a box. That's what that top spaghetti graph is doing. So we generate those annotations, and then we format to whatever format we need to make it in. In this case, you'll see below, I don't know if you might recognize that if you guys are in computer vision, but we get a text file out with the label that we want. And we can do that either per frame or for the whole sequence. And then you can see we have RGB, we have a segmentation mask, we have a world normal. Okay, so Taylor's going to talk a little bit more about that next.
So as you can see these images over here, right? We've got the RGB one, we've got the segmentation mask, and we've got the world normals. These are all done with post-processing materials. And sort of the same way Luis had mentioned those trigger events, we have essentially a child class of the post-processing volume that we can send we can send that events to, and we can say, hey, we want use this post-processing material, this one, right? So segmentation, depth, and even inside of those materials. So even inside of this one, right, you've got parameters, right, that you can adjust. So say you have a depth mask, you can change the actual the actual depth, right, the depth range of that sensor if you're trying to emulate a sensor. I will explain this one. But again, going back to this, some of your labels might not be, they might not be exported sort of as a CSV or text file. They might be actual images, right? Again, as we pointed out, segmentation mask in the world normal. We do that with the movie render queue. We got the RGB one. You might also want to, segmentation mask, and then I think world normals, and then we should get the depth mask, right? Just to show you, right? You can do all of this. You can generate this data at, running the same sequence, and just the reason we use sequencer. I've seen a lot of these Unreal sims, and there's no right or wrong way to do it, but a lot of them start with, essentially running as an application, or at least running in Pi. Sort of a real-time thing, which makes a lot of sense in a lot of use cases. For this one, we started off as we just want to generate data. That was our requirement. We need to generate data. Sequencer gives a lot of ability to save your sequencer. You can save that as using source control. So those data sets are reproducible. That's kind of a big deal, right? If I generate a data set and somebody, I'm in Huntsville, Alabama, you're in, Seattle. If I generate a data set, you should be able to generate that same exact data set on your machine. And that gets into more of the verification and validation aspect of it, but sequencer is very useful for that. And then, of course, you can see these just all the different things you can do with post-processing effects. I guess the most important one here is probably that top one, right, the smallest one, obviously, so it's the most important. The cutout background, that was kind of like a gold thing, right? You used to be for if you're doing like domain randomization, right? If you've got your object cut out, right, and then you can put whatever images you want behind it. Again, we try to stick to actual, full 3D, environments. So here we've got, this is just a simple semantic segmentation post-processing material. Everything in that big gray box is just baked down into a material function you'll see below, that MF, what is that, depth hard-coded. And then the top left, we've got our label number, this is label 1, and then we've got our color for that, which again, 8-bit, single channel label. If your object has a label of 1, it's going to come out as white. And then at the bottom, right, we kind of package this all up. If you're label 7, it's going to come out as kind of a dark gray. And I'll just, from my experience working in this field, this is another area where it's very easy to be like, oh, okay, well, I use an 8-bit image, and you can support, essentially 255, unique actors for semantic segmentation, and then 0 for background. You might say, oh, well, why don't we use a 16-bit EXR, and then we can do 16,000. Again, just a little advice like this: if you can manage 12 actors, 10, 12 actors, that's probably 80% of your use cases, and everything else is going to be some sort of unique solution. And that also makes it human legible, right? So somebody can get these labels and they can tell the difference between different ones, right? So if we labeled 1 255 and we labeled 2 254, depending on the monitor you use, that's virtually impossible to tell a difference. So it does kind of maintain that human legibility aspect. And then on your static mesh actor, you want to make sure the render custom depth pass is enabled and that you set that custom depth stencil value. That stencil value is essentially your label number. And then you want this any of your labeled post-processing materials, you want to happen after the tone mapping. So in kind of the render pipeline, the tone mapping is what happens last. If you do that, I think by default, it's going to try to do it before. You're going to get all kinds of bloom and lens glare and all those kind of post-processing camera effects you don't want. Also, the other thing is obviously don't save your labels as lossy images like JPEG. Right? You want something like a PNG image. It will give you. I've seen it. It'll give you a headache. Okay, so hardware emulation with the Cinecam. This is just, I don't know, this is near and dear to my heart. This is just very cool stuff. So with this Cinecam, we used to years ago, it's like, okay, we can match the field of view and the aspect ratio. And then as Epic has gotten into this virtual production, they have released a ton of useful tools for this. So the Cinecam you can match. Again, you've got sort of camera, you might have its specs, like its sensor width and height, its focal length, those are kind of the big ones. If you have those, and just so you know, these values here, this is just a Nikon Z5 camera with a 35 millimeter lens. And this video is a Z5 camera with an 80 millimeter lens. Right, so it's very easy to match those. And I guess the other thing is, when you take an image inside of the Unreal Engine, or with any virtual camera, it's going to be a perfect pinhole camera, right? So you're not going to get any type of lens distortion. A lot of times this is what you want, right? Because if you have a computer vision model, a lot of times there's going to be a post-processing step where you try to undistort that image, right? You've used a calibration board, you've calibrated your camera, you've got the camera intrinsics, you then use that information to remove that lens distortion. So this can be a good thing unless you're at the point where you're doing full H-will, like hardware in the loop, right? So you actually want what the camera should theoretically see. That's where this little lens component comes in. So if you can add this lens component to the Cinecam actor, some of you might recognize these values, K123, P12, FX, FY. That lets you capture the distortion of your camera. So you get proper camera distortion there. Again, this is if you're doing full hardware in the loop. You have to manage your color space. And I feel like in this slide, I didn't do it justice, but there's a video by Rod Bogart for from I think pixel to the pipeline of a pixel. So it's from the Unreal Fest 2024. It goes into detail about this using OCIO to manage that color space. Again, absolutely critical that you understand that. We didn't go into it here. Yeah. Thanks for your time. You kind of just lose. Any questions?